Today, we're going to learn how to calculate MN. This is the moment capacity of a cross section. Okay, so we're going to learn how to calculate the moment capacity. And it's complicated a little bit from what you've learned in your basic engineering classes, in that the stress distribution of the concrete compressive force is nonlinear. And as we said last time, we're going to replace that with the Whitney stress block. So what we'll have, if you remember, is there will be a neutral axis C, but the stress block will be over a height A, and the stress on this rectangle is 0.85 F prime C. And if we've detailed the beam correctly, we know that the steel is yielded, so that will be Fy. So here are the stresses. And what that will mean, we learned last time, is that you'll have this compressive force C, and you'll have this tension force T, and the distance apart we call Z, and the tension force will be just the yield stress times the area of steel, and the compressive force is just going to be the stress of this rectangle, 0.85 F prime C, times the area that it's acting on, the width of the beam times this height A. And so we're going to use this free body diagram to get MN. Before we dive into that, I want to compare analysis versus design. So in analysis, you have all the information given. There's one answer, and the solution is very straightforward. You can even make a little step-by-step procedure. Okay. Opposed to this, or in contrast to this, design, you don't have all the data, and that's why you're designing. You're gonna decide some things. There's multiple answers. Not all the answers are the same or need to be the same. There's several acceptable solutions, and the solution is iterative. So calculating MN is an analysis, okay? So this is what we're gonna do. It's very straightforward. So because it's analysis, there is a procedure, and steps 1, 2, 3, use T equals C to solve for A, the depth of that stress block. The moment arm between the compressive and tensile force, that couple, is Z. It's just the distance from the steel to the top down to the center of that rectangle, so D minus A over 2. And then finally, M equals T times Z or C times Z. It doesn't matter because C equals T, and T is easier. It's just FYAS. Okay. So C equals T. Let me go get that free body diagram. Okay. Copy that. Bring it down here. Okay. So the compressive force is just that stress, 0.85 F prime C, times its area, this width B, and the depth of that stress block was A. Okay, so this is the area. For the steel, the stress is Fy. We've designed the beam properly, so it's yielded. And the area of steel, of course, is just AS. Solve for A. There you go. Okay. Just solve that equation for A. Next, Z is D minus A over 2. So if you remember, that distance was A for the compressive stress. And that's going to be T. So this compressive force is at the middle of that rectangle, okay? So the distance from the top to the steel is D. So that means this distance here is D minus A over 2, right? You come down to the middle of that rectangle. So Z is D minus A over 2. And then finally, Mn is T times Z. So I like this one, FYAS, that's T, times D minus A over 2. Okay, so here's a basic example. Okay, so have 1.8 square inches of steel. Okay, so you look it up, 3 number 7 bars equals 1.8 square inches. Okay, you can look it up in a table. So T is just 1.8 times Fy, grade 60, so 60, that'll equal 108 kips. Okay, A, so 0.85 F prime C, B times A equals T, right? Fy, C equals T. Remember, C equals T. So 0.85 F prime C is 4 KSI. The width is 12. And we just got that T was 108 kips. Solve for A equals 2.65 inches. Okay. D, that was, D is, oh, we have to talk about this. If it's 18 inches from the top to the bottom, it's about, the middle of the steel from the bottom is about 2.5 inches. So 18 minus 2.5 is 15.5 inches. Okay, so Z is D minus A over 2. Okay, that equals 14.18 inches. And finally, Mn is T times Z. Okay, so we already got T up here. So 108 times 14.18, that equals 1531 inch kips. The reliable strength is 90% of that. Phi for flexure is 0.9. So 0.9 times 1531. And usually we want it in kip feet. So I'm going to divide that by 12. This is kip inch divided by 12 inch per foot. That equals 115 foot kips. So you can have 115 foot kips of moment reliably put onto this cross section here. Okay, that's pretty straightforward. If you want to see how I would write it out longhand, you can keep watching. Otherwise, what I'm going to do now is just repeat. So what I would do is, if I was solving this, so I would have this. It was 12 inches. The area of steel was 1.8 inches squared. This distance here was 18, which means that this distance here is 15.5. Just subtract 2.5. Okay, so if I was to solve this by hand on paper, I'll go, oh, T on F prime C is 4 KSI. Fy is 60 KSI. Okay, so if I was solving it by hand, I just go 1.8 times 60. So that is, so hopefully I get the same answer, 108 kips. A is 0.85 F prime C times B all over T. Okay, I just did that in my head. You know, it's 0.85 F prime C B times A equals T, C equals T. And I just put, oh, see, it's a good thing I double checked. I did that wrong. So it's T, 108 kips, divided by 0.85 F prime C times B, which is 12. Okay, so I'll run that out. Uh, 2.647 inches. Okay, Z is D minus A over 2. 15.5, 2.65 divided by 2. Subtract that, 14.18. And Mn is just T times Z. Uh, 1,530. I'm rounding. I think it's 31 or something. And so phi Mn, and divide that by 12. 127.6 kip feet. And so phi Mn is 90% of that. So that you can reliably count on 115 foot kips. Cross our fingers, and yes, we got the same answer. Okay, so in real time on a piece of paper, that's how that solution would look like.